Hi students, it's Dr. Marks and our topic for today is confidence intervals. But gang, we're going to take this in smaller chunks. So this particular lecture is simply going to focus on what they are and not how to construct it. We'll move on to that after we cover this topic. Now, if you remember, in our introduction to statistics, we discussed the idea that the field of statistics is divided into two parts. We talked about descriptive statistics, and in modules 1 and 2, we've spent a lot of time talking about descriptive statistics. We've covered mean and median and mode and standard deviation and things like correlations. But now we're moving into the area of inferential statistics. So inferential statistics is going to be our topic for the rest of the class. Keep in mind that inferential statistics is different from our descriptive analysis. Remember, we're no longer describing data. So if you think about what we've been doing, we've taken samples and we've just looked at how they appear. They have a mean, they have a standard deviation that's big or small. We can use some data visualization to give a pictorial representation, right? And so we spent a lot of time simply describing data. But now we're using data from our samples to learn about the population. Remember, we've talked about that we're taking samples with the goal of learning about the population because our population might be too large. We can't simply sample every single person or survey every single person in the population of interest, and hopefully our samples can teach us more about what our population looks like. So that's where we get this word inferential from. We're using our samples to infer, to learn about the population. Back to our definition. We've seen this a few times, but let's just remind ourselves. We've talked about statistics as the science of collecting, describing, and interpreting data. So we've talked about collecting, right? Data and data collection back from module 1. Describing, we've covered descriptive statistics, and now we are interpreting data. And again, our definitions for descriptive statistics and inferential statistics. Descriptive statistics was the collection, presentation, and description of sample data, whereas inferential statistics is making decisions and drawing conclusions about the population. So clearly, inferential statistics is going to be a little higher ordered. It might get a little bit challenging. It's certainly going to be a little bit more complicated than descriptive statistics, but we're going to go through it slowly, and hopefully everyone will be able to follow. One type of inference that we're interested in is the confidence interval. So when we talk about a confidence interval, we collect samples, and then we get statistics, right? We've been talking about sample means. And from that, we want to learn about our parameters. And remember, the term parameter, that describes a population. So I just want to remind you about just terminology. When we talk about statistics, when we use the term statistics, like this is a statistic for, statistics are referring to samples, but parameters are referring to populations. So when I have a mean for a sample, it's a statistic. I want to use those sample means to infer about the population mean, which is a parameter. Remember that parameters, again, from our population are unknown, right? We generally don't know the population mean, for example, because it could be incredibly difficult for us to survey an entire population. Now, if I could survey an entire population, then I would know the population mean. But if we're talking about all college students in the United States or smokers in the United States, right? I can't possibly survey that entire population, but I can take a sample. So we want to make inferences, and we make those inferences based on our sampling. So this should be review, but this is kind of where we're heading in this idea of using our samples to make inferences about our population. So what is a confidence interval? You've probably heard the term confidence interval before. You definitely used it once upon a time in your statistics courses, but maybe you can't really articulate it. And we want to work on articulating what these things are and what they mean. Now, in my opinion, it's best, at least initially, to think of these two words separately. We have one element talking about confidence and the other talking about interval. The interval part means that we have a range of plausible values for the parameter. For example, maybe we estimate that our population mean falls between 2.45 and 3.87, right? So we have this interval of possibilities. Well, that's the interval part of confidence interval. But we also have to address confidence. And the term confidence is referring to the degree of certainty that we have. So we have an interval with some degree of certainty. These two things are going to turn out to be linked, that our confidence and our interval width are going to be related. And I'm going to show you that. So you're going to see that. And I appreciate that this is still very abstract and you might be a little confused and you're saying, hey, Dr. March, I'm not getting this. Stick with me, please. I will get you there. Keep in mind, gang, that samples are random by nature, right? We're taking random samples. And because these samples are random, it's unlikely that two samples from a population will give us the identical confidence interval. Well, hopefully they're not drastically different, right? Because samples should be similar, but they're probably not identical. However, if we draw many random samples, right? We may not just draw one, but if we draw many random samples, then we can get a bunch of different confidence intervals. And a certain percentage of the confidence intervals will contain this unknown population parameter. I know that's a little confusing. So again, we take a bunch of samples and we have a set of confidence intervals, and there's going to be some percentage of those confidence intervals that will contain this unknown population parameter. For example, like the population mean. The percentage here that we're talking about is the confidence level of the interval. So, still a little vague, I know. Let's look at what a statement could appear like if we were looking at some research. Maybe somebody says, we are 99% certain that most of these samples contain the true population parameter. All right, well, what are they talking about? Well, when they say 99% certain, they're talking about the level of confidence, right? We're talking about confidence intervals where confidence is talking about how certain do we think we are. Well, if somebody says they are 99% certain, they're saying we're pretty darn certain that most of the samples that we've collected contain the true population parameter. When they say contain the true population parameter, they're saying that they fall within the interval. All right, so that's talking about really this idea of we have a range. I know it's still vague, so let's firm it up a little bit by looking at a diagram, and I love pictures. So here's a whole bunch of different samples, right? We've got 20 samples that are taken in this investigation, and you can see them numbered 1 through 20 on the left side of the picture. And we have mean and standard deviation for each one of these samples, right? If I take a sample, I can calculate the mean and standard deviation. And let's assume 95% confidence, right? So in the last slide, we talked about being 99% confidence, but here we're going to back off just a little bit and say, okay, I want to be 95% confident. That's pretty darn confident. So that means that each interval, this confidence interval, was constructed for 95% certainty. Now remember, we talked a little bit about the fact that certainty, the level of certainty, is going to affect that width of the confidence interval, and I come back to that. But if you look at a particular confidence interval that's constructed, it's under the assumption I want to be 95% confident. All right, so we've got this set of confidence intervals here. Guys, do they look identical? No, because each sample is going to be a little different. But if they looked drastically different, if they were just way all over the place, then that would be a problem. So let's look at this, and we see at the top, I show you the distribution, and you see that dotted line where we have the population mean, mu. That population mean, which just follow the dotted line straight down, those don't quite line up just exactly right, but you see the population mean in the dotted line and assume that it kind of just follows all the way down that line. Do you agree that the population mean falls within 19 out of 20 of the confidence intervals, right? The confidence intervals, again, are those blue lines. Those are showing the range. And do you agree that that population mean is within the blue line for all but one of these 20 confidence intervals? So only one sample fails to cover the population mean, and you see that in the red circle. So I've circled for you the one sample where the confidence interval does not contain the population mean. So with 95% confidence, we can say that we're expected to be right 95% of the time. That's really what we mean when we say we want to be 95% confident. We want to be right 95% of the time. Now, hopefully you're thinking, well, why not 99% of the time? I'll tell you the answer to that question in a minute. Do we agree that in this illustration, they are right 95% of the time? Why am I saying that? Because 19 out of 20 of the confidence intervals contain the population mean. So 19 out of 20, I guess I could say got it right. If 19 out of 20 got it right, you do the math. If I take 19 divided by 20, right? If you don't believe me, just do it on your calculator really quick. I'm doing it on mine. And what do I get? 0.95, 95%. So in this case, they are right 95% of the time. Hopefully this depiction right here has firmed up this idea of a confidence interval. So just quickly to recap, a confidence interval is a range, right? We see that here. Some of them are wider than others, and it's kind of a range that most of these overlap a little bit because samples are different. Not every sample is going to be identical, but they are reasonably similar, right? If they were drastically different, that would be a problem. All right, we probably have firmed up a little bit this idea of confidence interval. So let's keep going. Now, before we continue, gang, I need to make sure that you do not misinterpret a confidence interval. We are not saying that 95% of our data falls in these intervals, right? That is not what we're talking about. If you think about what we just talked about with that picture, I never said 95% of the data falls into these intervals, right? That would be a correct statement. Instead, and that would not be a correct statement. I think that's what I just said. What we are saying is that the true population parameter, mu in this case, the population mean, falls within the confidence intervals 95% of the time. In other words, we're saying we are right 95% of the time. This is a really important point. So let me just give you a second to absorb this. I'm going to repeat it, and then I want you to think about it for just a moment. So we are not saying that 95% of the data falls in these intervals. Again, that would be an incorrect statement. Instead, we're saying that the true population parameter, we've been talking about the population mean, mu, falls within the confidence intervals 95% of the time. We're not talking about data, right? So we're right 95% of the time. We're not talking about all of our observations. We're simply talking about the population mean falling within the confidence intervals. All right, let's move on. But ponder this for just a second. Make sure this is clear. I found a great fishing analogy that might help some of you understand, why do we even deal with confidence intervals? What is this about? Well, we could use a single point estimate. And when we use the phrase point estimate, we're talking about something like a sample mean. We've got this kind of single observation. I take a sample, I get a mean, and I have that single point estimate. And that's an approximate value of our unknown parameter. Remember, our unknown parameter is that population mean. So we can take a sample mean and use that as kind of an approximation of our population mean. But in this wonderful analogy that I've stolen from somebody else, it would be like fishing with a spear in a murky lake. Now, why do we say that this would be like fishing with a spear in a murky lake? Well, that's because we can throw the spear where we see the fish, but we're likely to miss, right? Think about trying to fish with a spear. It's difficult. It's hard to get it exact. I have to be very, very exact if I want to take my spear and get the fish, right? A confidence interval, unlike a spear, is like fishing with a net. Now, with a net, do you agree it's going to cover a wider area? And so if we cover a wider area, we have a good chance of catching the fish. So instead of the spear, where I just have one number and I'm trying to be exact, instead, I'm going to cast a wider net. And if I cast a wider net, I have a better chance of catching the fish, right? So if we report a point estimate that's based on our sample, right? If I just report a sample mean, then I won't likely catch the exact population parameter. You know, it's an estimate, it might be close, but it's not as likely to be exact. But if instead we report a range of possible values, right? That range of possible values is like our net. That's our confidence interval. And that range of possible values is going to be based around our statistic from the sample. In other words, I have a sample mean. And so if we just go a little above and a little below, then we have a good chance of catching the parameter. So just looking at a sample mean might not make it very easy to get it right. If I cast a wider net, I'm more likely to catch the fish, or I'm more likely to hit upon the true population parameter, like the population mean. So basically what we're talking about here is creating a confidence interval that captures a margin of error, right? So look at this diagram for a moment. We have an estimate, right? Where does that estimate come from? Well, that estimate could be our sample mean. So I've taken a sample and I have a sample mean, but that sample mean may not be exactly the same as our population mean. So I look a little above and a little below, and that's that idea of margin of error. So if I take my sample estimate, go a little bit above, a little bit below, right? That's that plus or minus we just talked about in the previous slide. Now I have a confidence interval. That's really all we're doing here. We're giving ourselves an opportunity to say, okay, this point estimate, the sample mean, may not quite get it right, but if I look a little to the left and a little to the right, I increase the probability that my population mean is within this range. All right? Hopefully this is starting to make sense to you. let's look at some real-world examples of confidence intervals. And I went online to try to find some good examples, and I found one. It's a little old. It doesn't matter. It's from 2008, but Gallup did a survey, and Gallup was interested in comparing mean well-being for people with and without televisions. That's kind of an interesting question. For me personally, love my television, have probably too many of them, but maybe people without televisions are actually, better off. They have higher well-being. And so the part of the study that I'm looking at was the European part of the study, and they made some interesting conclusions. So for the European part of the study, the Gallup poll concluded based on their surveying. Remember, they're taking a survey, which is a sample, and trying to infer something about the population. So their study said one can say with 95% confidence that the true population for well-being among those without TVs is between 4.88 and 5.26. So what are they basically telling us there? They're saying, hey, we didn't survey everybody in the population. That would be impossible. We took a sample of people without TVs, and we feel that if we look at the sample mean and then go a little above and a little below based on some things that we're going to learn in the next lecture, we can say with 95% confidence that the population of people without TVs, well, their well-being falls within this range, 4.88 to 5.26. So do you see what we're doing? We're giving ourselves a little margin of error there. Then they conclude for those with TVs, right? So the previous statement was about people without TVs. For those with TVs, the 95% confidence interval for well-being is much narrower, between 5.78 and 5.82. All right. So gang, we see some interesting things there. First of all, we see that the first confidence interval, people without TVs, is wider. And the confidence interval for people with TVs, when we're measuring well-being, it's narrower. But also, do those confidence intervals even overlap any? No, they don't. So you can imagine that this study goes on to talk about probably that people with TVs had a higher well-being than people without. But again, what the study's doing is being very careful to say, look, we're assuming a 95% level of confidence. We want to be right 95% of the time. They could have said 99%, but as we're going to move on to look at in just a second, that would change these intervals. All right, this is just an example. Hopefully it makes sense to you. Let's think about another example. Maybe you're in the medical profession and you're conducting a medical study where you collect a random sample of heights from the population. Now again, we agree if we want to learn about heights of Americans, for example, we cannot possibly survey the entire population. Instead, we're taking samples and we determine that the mean is 74 inches, right? So let's just say we take one big sample, 74 inches, but we agree this is the sample mean. We can't say that the population mean is 74 inches, but of course, remember, what's our goal here? We want to use our sample to infer about our population. But we don't know how far off this is from the population mean. It's not likely our population mean is also exactly 74 inches. Remember, gang, the population mean is unknown, and we're using our sample to try to see what we can infer about the population mean. So given that we don't know the population mean, but we have this sample mean, we want to construct a range that we think will capture the population mean. And that's that idea of the interval, right? That's the interval part of the confidence interval. But we also have to decide how certain we wish to be, because that's the level of confidence. And so far, I've given you examples where we've talked about 95% level of confidence and 99% level of confidence. And those are going to be a little different. Do you want to be right 95% of the time or 99% of the time? Let's say in this example, we want to be 95% confident. Now, I agree that's not as good as being 99% confident, but please understand, and I know some of you are researchers and you already know this, that if you were doing a study reporting results at 95% confidence, that would be strong. 95% confidence would be good. No one's going to go, ugh, only 95% confident. That's not a very good study. So just trust me when I tell you that. For us to be able to proceed here, we would need our sample mean and our sample standard deviation. But we have these, right? We have been talking about how to calculate a mean and a standard deviation in our descriptive statistics. So once I take my sample, getting those very easy, right? And we're assuming a normal distribution. So we have to remember, all right, we're working under the assumption that this is a normal distribution. Keep in mind, the normal distribution has properties that we know, and that's going to be important when we start learning how to determine the confidence interval. Now, from our assumption of normal distribution and our mean and our standard deviation, from those pieces of information, we can get our upper and our lower bound for our range. So, for heights, maybe we get a confidence range from 72 to 76 inches. I have a upper bound of 76, a lower bound of 72. This means that with 95% confidence, if we take 100 random samples, again, from the population, the mean should fall between 72 and 76 in 95, at least 95 of those samples, right? For me to be 95% confidence, then the population mean should fall between 72 and 76 in 95 of those 100 samples. So that's what it means to be 95% confidence. Please note, at this point, we don't know how I got this interval, right? You don't know how I got 72 and 76. And we're not worried about that at this very moment. For right now, we're simply interpreting the idea of confidence intervals and understanding what they are and why we think in this manner. But what if we want to be even more confident? As I told you, 95% is a pretty good level of confidence, but I could certainly strengthen that to 99% confidence, for example. But here's the deal, and hopefully earlier you were thinking, well, why not just always be 99% confident? Here's the deal. There is going to be a trade-off. And that trade-off is that we're going to have a broader range. You want to be more confident? Broader range. So maybe now, if we want to be 99% confident, our confidence interval goes from 70 to 78 inches. So if we take 100 random samples, again from the population, then what we're saying is the mean should fall between 70 and 78 in 99% of those samples. Hopefully that makes sense, right? Everyone can understand what we mean. But let's compare now. As we've talked about before, confidence intervals, that range, connects to confidence levels. These are interrelated things. We have to ask ourselves, how statistically sound do we want to claim our results are? To be more certain, the confidence interval has to be wider. That's the trade-off. To be more certain, the confidence interval has to be wider. So take a look. When we were talking about 95% confidence, our range was that heights would fall between 72 and 76%, inches, 72 to 76 inches. But if I want to be 99% confident, then our population parameter is going to fall between 70, not 72 anymore, and 78, not 76. So do you see what's just happened there? Our confidence interval at 99% has gotten wider, right? It's gotten wider. Let's look at this with a picture. I love pictures. So if we're 95% confidence, we have an interval. But if I want to be 99% confident, I need to have a bigger range. That's the trade-off. You can kind of narrow in on more precision with 95% confidence, right? Because it's going to fall within a smaller range. 99% confidence, I have to give myself a little more wiggle room. In other words, that margin of error has gone up a little bit. As it says at the bottom, if I want to increase the chance that I catch the fish, if I want to be more certain that I catch the fish, I need a bigger net. That's all we're doing here. I want to be more confident. I need a bigger net. Widening the range of that confidence interval is like getting the bigger net. So very quickly, gang, at this point, we understand the idea of a confidence interval. You have a general sense what we're trying to do. We're fishing with the net. And you understand that the width of that confidence interval depends on our level of confidence, right? We understand that if we want to be more confident, that interval gets wider, fishing with a wider net, a bigger net. At this point, we've not yet learned how to determine the confidence interval. We've interpreted it, but you don't know how I got 72, 76, 70, 78 when we talked about the confidence intervals for the height example. You don't know where we got those from because we haven't covered that yet. For us to determine the confidence interval, we have to go back to our normal distribution. Remember that bell-shaped distribution that we've worked with a few times, we've looked at? And we have to rely on those characteristics that we know a normal distribution has. And that will allow us to get these ranges, create the confidence intervals. That's our topic for the next lecture. So please let me know if you have any questions on this. Please do make sure you understand the basics here before you move on to the next lesson. Thanks so much for listening, gang, and have a fantastic day.